In this video, I'm going to talk about Ksp calculations. First of all, it has to be mentioned that Ksp is nothing special but a KEQ, especially for the solubility equilibrium. Anytime when we have a saturated solution, when the rate of dissolving equals the rate of crystallizing, which means we have a saturated solution, then a solubility equilibrium exists. Ksp is just the KEQ for this special equilibrium. There are three types of Ksp calculations in general. Type 1 is the easiest. So type 1 type of question will be involving just a saturated solution of a compound. No other substances are present, so there's only one substance which has achieved solubility equilibrium. Then just a saturated solution. But different types of salt, they will have different relationships between their Ksp and their molar solubility. One thing to emphasize here is Ksp is ultimately an KEQ. So with all the Ksp calculations, you have to use molarity as the unit for the solubility. You can't use anything else. Anything else you have to convert them into molarity to plug in the Ksp equations. But different types of salt will have different relationships between Ksp and molar solubility. Like in the case of silver chloride, because silver chloride dissociates into one silver ion and one chloride ion, you can see the Ksp equals to the solubility to the power of 2. So it is true for any AB type salt. The Ksp equals solubility squared. For a salt like PbCl2, in here, each PbCl2 will dissociate into a Pb2 plus and 2Cl minus. Here you can see because of this extra 2, then the concentration of the chloride is 2 times the concentration of the lead, and because of the nature of the KEQ, you not only have to double the concentration, and also you have to power. The power has to be squared too. So in here, if you have a AB2 type or A2B type salt, then the Ksp will be 4 times solubility cubed. Similarly, if you have a AB3 type or A3B type salt, the Ksp would be 27 times the solubility to the power of 4. So once you identify what kind of salt you have, and then the relationship between the Ksp and the solubility can be established, and you can converge between Ksp and molar solubility back and forth. So if they're asking you about any unit that's not molarity, then once you get the molarity from Ksp, then you can convert the molarity to whatever unit you need. Another thing to be aware is since Ksp is a KEQ ultimately, so Ksp doesn't change unless there is a change in temperature. The solubility has a given relationship with Ksp. So if you have only a saturated solution, no other substances involved, then the solubility of a given substance would also be a constant at a given temperature. Here is an example of type 1 calculations. So if I know the Ksp of PbCl2 at 25 degrees, then I can calculate the molar solubility of PbCl2 by plugging the equation between Ksp and the solubility equations. In this case, it's an AB2 type, so the Ksp should equal to 4 times solubility cubed. And since we already know the Ksp, the concentration of the PbCl2 can be figured out. Type 2 calculations involves the presence of a common ion. So a common ion is something you have a saturated solution, but the solvent is not only water. In that solution, you also have something that can dissociate and produce the ions in your solubility equilibrium. So like in this example, so what's the molar solubility of PbCl2 in 0.1 molar magnesium chloride solution? In this question, you not only have lead chloride, you also have magnesium chloride. So the magnesium chloride will dissociate and produce chloride ion. And because magnesium chloride has a 1:2 ratio between magnesium chloride and the chloride ion, if the concentration of the magnesium is 0.1 molar, then the concentration of the chloride will be 0.2 molar. Now when we are doing the ice table of the PbCl2 solubility equilibrium, you can see even like before the dissociation of the lead chloride, you already have 0.2 molar Cl minus coming from the magnesium chloride. If X molars lead chloride dissolves, then you're going to have X molars lead 2 plus and 2 X molars chloride added to the original mixture. So in the end, your concentration of lead 2 plus will be X, and the concentration of chloride will be 2X plus 0.2. So when we plug this into the solubility Ksp expression, then you can see we have an equation that's not that easily solvable because it's a quadratic equation, or even more than a quadratic equation because I have a square there. To simplify the question, we can always assume, because the low solubility compound, the Ksp is already very small, so we can assume with the presence of the chloride, which doesn't help the equilibrium to go towards the product side, we can always assume X is a very small number. If X is very small, then 2X plus 0.2 would equal to 0.2. So now once our equation has been simplified, we can find out the concentration of the lead chloride, which is the X, to be 3 times 10 to the power of negative 4. From here, you can see due to the addition of the magnesium chloride, the solubility dropped from 0.014 molar, as we calculated earlier, to 3 times 10 to the power of negative 4 molar. So for the type 2 question, you can always assume the common ion concentration would be the concentration that's being introduced by the other species. Like you can always assume the common ions concentration is the same as what has been introduced, like the ion like that come from your low soluble substance can be ignored. Another type of question would be like, what's the maximum lead concentration in 0.1 molar magnesium chloride? If we have trial Ksp, if we calculate the trial Ksp, and if the trial Ksp is greater than Ksp, then the precipitate will form. Magnesium chloride, in this case, again, will produce the chloride ion. The Ksp expression is Pb2 plus times chloride squared. And now, because we already have the chloride from the magnesium chloride, then now, since Ksp doesn't change, we already know the chloride concentration. We can find out the lead concentration. This lead concentration is the borderline concentration. Once the lead concentration is greater than its concentration, then the reaction, like the trial Ksp, will be greater than Ksp. In that case, like a precipitate will start to form. The last type of question is to predict whether a precipitate will form or not when two solutions are mixed. One thing I always remind my student is anytime when two solutions are mixed, always use M1V1 equals M2V2 to find out the new concentration of each species. Once you find out the concentration of each species, you can figure out the concentration of the relative ions. So if the trial Ksp is greater than Ksp, then the precipitate will form. If the trial Ksp is less than Ksp, then no precipitate will form. So in the following example, will a precipitate form when you mix the two solutions? First of all, we have to write out the equation to identify which precipitate we are dealing with. By looking at the equation, we know PbCl2 is this precipitate that we're going to deal with. Then before we do anything, we have to use M1V1 equals M2V2 to find out the new concentration of the PbNO32 and the new concentration of magnesium chloride. And then we will use the dissociation of lead nitrate and then magnesium chloride, which you can see here are both one-way arrows because they're soluble ionic compound. So they completely dissociate and produce the corresponding ions. Then from these two equations, we can find out the concentration of the lead 2 plus. We can also find out the concentration of the chloride. Then we can plug in the trial Ksp expression, which is the same as the Ksp. It's just that the ion concentration here, we don't know whether they would, they're just a combination of concentration at any condition. So we wouldn't call this Ksp, rather we would call this a trial Ksp. Since the Ksp after calculation is less than the Ksp, so we can conclude that there will be no precipitate being formed. Thank you very much for watching this video. Talk to you later.